Greetings to you. This is Lynnate Nazziwa, together with my colleague Marvin Benjamin Kivumbi, students at UTM. This is our first assignment in mechatronics design, and it's majorly about system modeling and analysis of a two-way balancing robot. First, we'll start from this other slide that has the derivation of differential equations from the first principles of the system. And the first bit shows the robot body and how it's later broken down into the different equations for the body of the robot and the wheel. Deriving our equations, our different equations, we are able to come up with state space equations, which is 4.22a and 4.22b. The first equation is in time domain and the second equation is in frequency domain. Now moving on from there to do the simulation in MATLAB, we are able to use the different parameters from the datasheet of the particular motor that we are using, and this is what is listed down here, the MATLAB file. For example, the different parameters for armature resistance, for armature torque constant, for armature back EMF constant, and the moment of mass of inertia of the wheels, the radius of the wheels, the mass of the body, distance from the center of gravity of the body, and many others. So after writing down all that seem to be our constants from these two equations here, we are able to write our matrices as well in MATLAB, which come up in a format A, B, C, and D as listed below. We are also able to call out the function, which is the transfer function here of the state space, and finally we are able to plot. So when we run our code in MATLAB, we are able to get different graphs of the different states. The first state is X, the second state is X1, as you can see from these matrices here. The next one is theta B, and the next one is theta B dot, which are different states from the state vector here. So putting that aside, we are also able to model the system in SIMULINK, which is right here, and our input is modeled basing on our input to the system, which is VA, this. So when we go to the SIMULINK model, our input is VA, which we are actually putting in as a step input, and our output is X, which is the displacement, and our angle theta B, which is the tilt angle of the robot body. And that's what we are feeding into our scope to be able to view the different graphs and behaviors of the system. So when we run, we are able to get this particular behavior on the dashboard scope. Then we shall also view more closely the behavior on the scope. This is considered for a case where we have an open loop system, in that we are not feeding back any information into our system. We only have inputs, the system, and the output. We are able to view our graphs right here for the different outputs. The one in blue is X, the one in red is theta B. And as we can see, the values of X exponentially grow big, and so do the values of theta b. They all grow exponentially big, but in opposite directions. And this shows us that as the system gets close to what we've set as our stop time, the system is still unstable. The system is still unstable, and hence a need for a mechanism of making the system more stable. To briefly highlight why the system would be called unstable, a stable system is one that produces a bounded output for a given bounded input. For example, for this system, we have a bounded input, which is a unit step function, which is right here. We would expect to get a bounded output, which is not the case. And also, an unstable system is majorly a system that's out of control. And as you can see, if we are to only change the time, for example, we come here and change this time to 10 and run the system again, you can clearly see that there is no change in the graphs, and there is no change in the shape of the graphs as well, meaning that for whatever time we put, the system is going to remain unstable because the curves, our two curves for theta b and x, only converge close and towards to the end time that we've put as our stop time. That shows us that the system is mainly unstable, and the only way we could make the system stable is by adding a controller. We could also try to put back the feedback of x right here back into this summing point, and as well put back the feedback from theta b into this summing point and see what happens. So putting back this, into this. So mainly we are feeding back our output x into the summing point, and also feeding back our theta b, this, into our system. And then we shall run again and try to observe the behavior of the system. As you can clearly see, the shape of the curves of our output, do not change. The only change we have is a difference in the parameters as to where the system converges. Before we had very big values to which the system converges, and feeding back the input right now only reduces the parameters at which the system converges. That does not either way make our system stable. So, putting all that aside, this explains to us, or proves to us, that we need to add a controller to our system to make the system stable. That means that for our robot to balance, we need to incorporate a controller into our block diagram, I could say, to ensure that there is stability at the end of it all. The examples of controllers we could use include the state feedback controller, or a PID controller. And in so doing that, would be able to have a more stable system and an easier way to balance the robot. Mainly to also take another analysis on our graphs that we have so far. This illustrates to us that if our angle theta b increases, then our x is going to be reducing, and vice versa. If our x increases, our angle is going to be reducing. Now that takes us back to the to the simple breakdown of the system that we earlier had. Yes, which is right here. So when the tilt angle is reducing, the robot is going to be moving in the x direction in a reducing value. For both directions, the values grow exponentially big with time since we do not have a controller in the system. Hence, a fundamental reason as to why we need a control system, and that explains to us that a balancing robot cannot work unless it has a control system. Thank you. What did you say was the command? Shift what? Windows Shift.